Alright guys, so we are working in Chapter 3, Section 6 today. Chapter 3, Section 6. Alright, Chapter 3, Section 6 is all about derivatives of inverse functions. Luckily, if you pay attention in algebra class, this shouldn't be too big of a deal. Actually, algebra and trig, I'll put that caveat in there. Algebra and trig class, this shouldn't be a big deal. It's actually, if you look in the book, it is 4 pages. Okay? It's a super short section, and I have here the main result. And we'll have a few more derivative rules to memorize after this. Here's the main results, okay, or results, I should say. Essentially, the theorem 3.16 says if you have a function that has an inverse, if f is continuous, then f inverse is continuous. Now we do have to recall in order for a function to have an inverse, it has to be 1 to 1. So if a function is 1 to 1 on an interval, then that means it has an inverse. So if f is continuous, then its inverse is also continuous. Likewise, if f has an inverse and it's differentiable on some interval, then f inverse will also be differentiable, assuming that f inverse at some value is not 0. Okay. Now, what does it mean to be 1 to 1? Just look at a really quick graph again, just to refresh your memory. So if you have a graph, a function is 1 to 1. If essentially the easy way to think about it is if every x value is assigned a unique y value. That is, there's no x value, there's no two x values that result in the same y value. So what do I mean by that? I mean by let's say we have oh, that's not what I wanted to do. Let's say we have negative 2 over there and positive 2 over there. If we had a situation where both of those mapped, say, to 4, so positive 2 maps to 4 and negative 2 maps to positive 4. If that was the case, that function is not 1 to 1 because we have two different y values mapping to the same, two different x values mapping to the same y value. So that's not 1 to 1. Now, when might that happen? It might happen when you have a function just like this. Okay, a quadratic function. Okay, a quadratic function is not 1 to 1. Okay, now the way we check to see, visually, to see if all of your x values are mapping to different y values, we have that thing called the horizontal line test. Remember, the horizontal line test says if you can draw a horizontal line anywhere on your graph and it intersect that graph in more than one spot, it's not a 1 to 1 function. So this is not a 1 to 1 function. So x squared does not in general have an inverse. Now we could do something like this. We could say, well, let's just restrict the domain of x squared. And you'll see this in some of the exercises we'll do. Let's say x squared only starts at x is greater than or equal to 0. We just restricted domain, kind of how we deal with piecewise functions where we restrict the domain and only graph it over certain x values. So there we go. So I think now you can see that it certainly would pass the horizontal line test. Any horizontal line you draw is only going to intersect that graph in one spot. Therefore, it is 1 to 1. Okay? So if you restrict the domain here, it is 1 to 1. Therefore, this would have an inverse. If I drew the entire thing like I did just earlier, like that, that's not 1 to 1, and that would not have an inverse. Okay? But if we had just the restricted domain like so, it will have an inverse because it is 1 to 1. Now, most of this stuff, since this section is about inverse functions, these are all going to have inverses. Okay? And here's the way we're going to find the derivative of an inverse function. Okay? Theorem 3.17 says, let f be a function that is differentiable on an open interval I. So that means the derivative exists for some function on an interval, maybe all real numbers or maybe not all real numbers. If f has an inverse function, that is, if f is 1 to 1, and it has an inverse function g, then g is differentiable for any point for which f prime at g of x is not equal to 0. Moreover, the derivative of our inverse function is given by this expression right here. So remember, g here is our inverse function. So it says the derivative of the inverse function is equal to f prime evaluated at that inverse function, provided the denominator is not equal to 0. Now, this tends to historically confuse the heck out of people. Okay? Confuse the heck out of people. But you just have to, just kind of with the chain rule, you just have to remember what it's saying. And I tend to rewrite this. With inverse notation, because I think sometimes it throws you off that you have f and g, and we forget that g is actually the inverse. So what I'll do here is I'll write f inverse prime of x. Now, that notation looks awful, but that is the notation. That's f inverse prime, the derivative of the inverse of x, of f of x rather, equals 1 over f prime at f inverse, so we have to use lots of parentheses, f inverse prime at x. Okay? So essentially what this says is, if you want to find the derivative, the slope of your inverse function at some point, you first need to find the y value that corresponds to x of your inverse function, which we'll show you how to do that, and then evaluate the derivative of f at that value. Now here's the kicker for this, is that we are going to deal with situations where we're given an x value of the inverse function, and we have to realize that that x value of the inverse function is actually a y value of the regular function. Let's look at an example, and you just have to be very clear about what value is in the domain of your original function and in the range of your original function, and what value is in the domain of your inverse function and in the range of your inverse function. Let's illustrate with an example. All right, so let's say we have f of x equals, let's just say 1/4 x squared, x cubed plus x minus 1. 1/4 x cubed plus x minus 1. Now, excuse me. Let's say we want to find the value, let's see here, find the value of f inverse prime at of x when x equals 3. Now this is exactly how a lot of your homework is going to go. So it's really important you really pay attention to the next couple examples here. So we're looking for the derivative of the inverse function when x equals 3. So we're looking for the slope of the inverse function when x equals 3. But notice what we're given. We're given just the original function. Okay? So there's a couple different ways to do this. The first way would be, I guess, to remember how to find the inverse function from algebra class. Okay? You remember and in fact, I just taught my college algebra students this last week. To find the inverse function, you have this like 4-step process. You replace f of x with y, you interchange the y's and the x's, you solve for y, and then you replace your newfound y value with f inverse. Now the problem is this function right here is not going to lend itself to that process. If we try to, let's say we try to follow that process. Okay, so over here we'll do some scratch work, and we would say, all right, we want to replace f of x with y, so we would say y equals 1/4 x cubed plus x minus 1. The next step of finding the inverse would be to swap your x and y values. Interchange x and y, so we would say x equals 1/4 y cubed plus y minus 1. The next step, so that's step 1, step 2, step 3 would be to solve this equation for y. But now we're to the exact same problem we were when we met with implicit differentiation. That is, we had equations that were not easily solved for y. So to solve this for y, it's a bunch of question marks. We're at a roadblock, okay? You know, if it was just like, maybe some sort of easy quadratic or a linear function, it wouldn't be hard to solve for y. But since we have a y cubed here and a y there, that's tough to solve, okay? It's not going to be pretty. So we're at a roadblock here. So if we want to find the inverse function's derivative, we would first need to find the inverse function if we weren't going to use Theorem 3.17. So we can't do that, at least easily in this case. So that's why we're going to have to rely on Theorem 3.17, because we can't find the inverse function easily. If we could find the inverse function easily, we would just find the inverse function and differentiate and plug in x equals 3. Easy as can be. Now, maybe I'll show you an example where that happens. But right here, we can't easily find the inverse, so let's rely on Theorem 3.17. So let's get into the process here. Let's apply Theorem 3.17. Now, to apply Theorem 3.17, we have to be very clear. We have to be very clear about one thing, and that one thing is what to do with x equals 3. Where does x equal 3 live? Okay, x equals 3. I'm going to draw a little chart for both things here. I'm going to draw a chart for f, and I'm going to draw a chart for f inverse. Now, f takes items from its domain, so we'll put a d over here and a range, d and a range. It takes elements from its domain and maps them to its range. F inverse reverses that process. F inverse takes elements from the domain, well, essentially the range of f, and maps them to the domain. So F inverse undoes the process that f does. All right, so let's think about this. This right here, that x value is in the domain of f inverse. So it goes right here. It's being mapped to something in the range of that function. Now, remember the relationship between f and f inverse. The domain and range swap. The domain and range of f and f inverse are just transposed. So if 3 is in the domain of f inverse, that means it has to be in the range of f. So the question is, what goes right there and what goes right there? It's got to be the same number, because the domain and range of f and f inverse are simply transposed. Now, we don't know what the rule for f inverse is. That's the problem. We hit a roadblock in our process over here. We don't know the equation for f inverse, but we do know the equation for f. So we need to ask ourselves, how do you get an output of 3? Like, how do you get 1/4 times x cubed plus x minus 1? How do you get that to equal 3? Now, the way I just do this, and you can do this with most of the examples we're going to work here, is just start guessing. Okay? If you plug in a 0, is f of 0 equal to 3? No. F of 0, let's just do this off to the side. F of 0 is equal to 0 cubed times 1/4, so 0 plus 0 minus 1. What's f of 1? And it might take you a couple tries to find this. If you plug in a 1, what do you get? Okay, well, you get 1 cubed, so that's 1, divided by 4, you get 1/4 plus 1 minus 1, so you get 1/4. What about f of 2? F of 2, okay, you have 2 cubed is 8. 8 divided by 4 is 2. 2 plus 2 is 4. 4 minus 1 is 3. So there we go. F of 2 equals 3. So that tells me that f takes the number 2 in its domain and maps it to 3 in the range. So I know automatically that the f inverse function is going to take the 3 in its domain and map it to 2. Now, why the heck did I just do all this? I did all this because I need it when I apply Theorem 3.17. Because 3.17 says this right here that I wrote in green essentially here. It says that if I want to find the derivative of the inverse function, I have to evaluate, do 1 divided by f inverse. That's just f prime. This is just f right here, so f prime of that, evaluated at f inverse of x. Oh, you know what? I just realized I wrote that wrong. There's nothing right there. F inverse of x, not inverse prime of x, because I don't know how to find f inverse prime. That's the whole point. Okay? So, let's see here. I can say, just to solve now, because I essentially have everything I need, I can say that f inverse prime of x, again, this notation I realize is atrocious, but that's just what we have to work with, equals 1 divided by f prime, so that's just this prime, evaluated at f inverse of x. Now, let us replace these x's with the value we're concerned with. Okay, we're concerned with x equals 3. So, like so, and like so. So what's this equal to? Well, this is equal to 1 divided by f prime. Well, what do we know that f inverse of 3 is? F inverse of 3 is 2. And now, that's not so bad, except I'm out of room here. This is 1 over, this says f prime. So pay really careful attention, like I didn't do over here, to the prime and inverse. That's a prime symbol, but guess what? That's just f prime. We can find f prime really easily. F prime, let's just write it down up here really fast. F prime of x is equal to what? Well, that's the power rule, so 3/4 x squared plus 1 is the derivative of f. So all we have to do is evaluate that derivative at 2 and we're good to go. So 3 over 4, 2 squared plus 1. Excuse me. So that's what? 4 divided by 4 is 1 times 3, so 3 plus 1 is 4, so 1/4. And there we go. 1/4 is the slope of the inverse function at x equals 3. That's exactly what we were looking for. Now, why is that kind of neat? That's kind of neat because we have no idea what f inverse is. Remember, we hit a roadblock over here. We have no idea what the inverse function looks like. Okay? But we know the slope of the inverse function at x equals 3. That's kind of cool. Okay? So we have no idea what the function is, but we know the slope at a point. And we can always find that using this method right here. Let's look at this graph real fast. Okay, so there is the graph of our original function f. Now, if we want to write the inverse, an easy way to do the inverse if you have some software like this is just to interchange the x's and y's. You don't actually have to solve anything if you just are using this nice software. So we could say x equals 1 divided by 4 y cubed plus y minus 1. So notice here, these are indeed inverses. You know, how do you know visually they're inverses? Is that they are reflections about the identity function y equals x. So these two functions are reflections across that identity function, and I think you can tell that that does work out pretty nicely there. Now, we contend that the slope, let's see, we found the slope of inverse, so we found the slope of that line at the point x equals 3. Okay, so x equals 3 is right here. We said the slope of that line, of the tangent line right here, was 1/4. Well, that looks about right. We can actually graph that real fast. Give me just a moment to work it out. Let's see, the slope was 1/4, so m equals 1/4. I'm just using point slope form here, and our point was what? It was 3, 2. So if we say y minus 2 equals 1/4 times x minus 3. So I'm not even going to simplify that. I just want to know what the graph looks like. I'm going to say y equals 1 divided by 4 times x minus 3 plus 2. And there is our tangent line. Okay? If we want to add in the points 2, 3, oh, it's actually 3, 2. There we go. Okay? So there is our inverse function that we don't know even what the function rule looks like. It is a function. It passes the vertical line test. We just don't know what it looks like. And there is our point 3, 2. So again, we found the slope of f inverse without ever actually finding the function f inverse. Now let's graph the original function. The original function was this red curve. Here's the neat relationship. The neat relationship is if at that point right there, slope is 1/4, that means at this point, kind of like the corresponding point on the original function, that the slope at this point has to be the reciprocal of the slope at that point. So if the slope right here is 1/4, that means the slope right here has to be 4. Let me see if that works out. Again, I'm just going to use the point slope form really fast. That would tell us that m equals 4 is what I'm proposing, and the point there is 2, 3. So we could say that y equals, okay, so this is going to be 4 times x minus 2 plus 3. Let's change that color, that tangent line. Let's say green. There you go. It worked out. So at this point, the slope is 4. That's my original function. At this point, the corresponding point on the inverse function, so this blue curve is my inverse function. You reverse the x and y coordinates. That's the corresponding points on both of those. Okay? The slope here at the purple point is 1/4. The slope here at the black point is 4. And that reciprocal relationship is always going to exist between the slopes of your original function and the inverse function. It's a pretty neat thing. Okay, let's look at another example of how this plays out. So let's see here. So let's do the exact same thing, but let's look at a different function. All right, so let's see here. Let's look at the function f of x equals, let's see here, 2x cubed plus x to the fourth. 2x cubed plus x to the fourth. Now, if we were going to go about algebra class methods, what we would do is that we would try to interchange x and y. We would then try to solve for y to find the inverse function, and then we would want to differentiate the inverse function and find the derivative. Oh, at what point here? I didn't write this down. We want to find f prime. Let's see. So there's our function. Sorry, I got ahead of myself. Find f inverse prime of 3. Okay? That is, we want to find the slope of the inverse at x equals 3. So slope of f inverse at x equals 3. So now let me pick up where I left off. If we were fortunate enough, we would be able to find the inverse function, and then differentiate that inverse function, and then evaluate at x equals 3. But I think we will learn that if we try to find the inverse function here, that's easier said than done. Let's just say we were going to try to do that. If we were going to try to do that, we would say, okay, step one is to replace your f of x with y. So y equals 2x cubed plus x to the fourth. And again, this is just straight up algebra technique here. Let's say step 2 would be to interchange x's and y's. We would say x equals 2y cubed plus y to the fourth. And now we're to that exact same spot. The next step is to solve that equation for y. But how do you do that? Okay, traditionally, if you have like two y terms, the goal is to get the y terms on one side and factor. But if we factor out this left-hand side, a y cubed, we'll still be left with the y term there. So it's kind of tough. So we don't know what the inverse function looks like. Okay? We don't know what f inverse is. So we would say f inverse of x equals, well, we don't know. Okay? So since that's the case, we need to use Theorem 3.17, I believe it was. Now, just to refresh your memory, 3.17 says the following. It says that f inverse prime of x is equal to 1 over f prime evaluated at f inverse of x. Okay? I wrote that correct this time. I didn't put the excuse me. I didn't put the inverse prime there. That was wrong. Okay? So, that's good. So, we need to do the exact same thing we did before, again being very careful with where this x equals 3 is and where that is it in the domain, is it in the range, is it in the domain of f or the range of f or the domain of f inverse or the range of f inverse. So what we have to be careful of is I like to draw these little charts. Here's my function f. And I'm going to write over here, there is f inverse. Okay, again, f takes things from its domain and maps them to its range, and f inverse does the same thing, except that the domain and range here are just going to be swapped. Now this right here, that x value is in the domain of f inverse. So 3 is getting mapped to something over there. Now, because of this, this relationship between a function and its inverse, if 3 is in the domain of f inverse, then 3 has to be in the range of f. And this blank right here, those are going to hold the exact same number, because the number that goes from the domain of f to 3 is the same number that goes from 3 to the range of f inverse. Again, that's just by definition of inverse functions. Now we need to figure out, so we can't figure this out directly. We have no idea what f inverse is right here. We ran into a roadblock. We don't know what f inverse of x equals. I mean, if we did, we would just plug in a 3 down here and get to the answer we're looking for. But since we don't know f inverse, we have to go to f and ask ourselves, what x value, if we plugged it into this, gives us a 3? Okay, well, let's just try a couple. I usually start with 0, maybe try a couple negatives, try a couple positives, and hopefully you can figure it out. Okay, f of 0 is 0 times 2 times 0 plus 0, so that's a 0. F of 1 equals, let's see, that's 1 cubed times 2, that's 2 plus 1, that's 3. Oh, so there we go, that wasn't hard. I wasn't expecting it to be so easy, but that wasn't bad. F of 1 is 3, so if you plug in a 1 here, you get 3. So there, we found out that the f maps 1 to 3. That means f inverse maps 3 to 1. Now that's essential for the process that we are about to complete here. Because now we're going to apply that formula, and this says that f inverse prime of x is given by 1 divided by, okay, f prime, we'll have to find that soon enough, evaluated, oh, you know what, I forgot to write my my numbers in there. There we go. Okay, so f inverse at 3, that's what I'm looking for, is 1 divided by f prime evaluated at f inverse of 3. Now, what's f inverse of 3? We just figured it out. F inverse of 3, f inverse maps 3 to 1. So we could say that this is 1 divided by f prime at 1. Now I suppose we have to break down and find f prime. Well, f prime, let's just find it right here. F prime, that's not hard to do. That is, let's see, 2x cubed. So that's 6x squared plus 4x cubed. So there's f prime. So we have to evaluate f prime at 1. F prime at 1 is 6 times 1 squared plus 4 times 1, oh, not 11, cubed. So what does that say there? That's 6 times 1 plus 4 times 1, so 1 over 10. So there you go. So here is the slope of f inverse at x equals 3, and we have no idea what f inverse is in general. No idea. But we found the slope of a point on its graph without actually ever knowing the equation of f inverse. Right here. I can't stress that that's what's important here. A lot of times people think this is a super boring chapter, but or a super boring section of chapter 3, but it's actually really interesting because we have no idea what f inverse looks like, the graph. We can't say, We can't say that f inverse equals x squared plus a square root of 2 plus 1. We have no idea. But we did find the slope, its derivative, at a certain point. Now, just for the heck of it, what does this tell me? What does this tell me that f prime of 1 is? This tells me that f prime of 1 is 10. Okay? Now, why is that true? Because the slope at this point is the reciprocal of the slope at this point. So we have 3 comma 1 over here. That's what I just found. That slope was 1/10. But I have the point over here, 1 comma 3, and the slope there has to be the reciprocal of the slope here. Slope here was 1/10. Slope here has to be 10. Okay? We'll verify that in just a sec. But before we do that, I want to show you one other alternative to finding this solution here. It's not, I don't think it's much easier at all, but it is another way to find the exact same solution. So here's an alternative approach. The alternative approach would be to like go here, where we were trying to find the inverse function, but we ran into a roadblock. Let's just say, okay, I can't go any further, but let's just stop trying to find the actual inverse rule, but let's just use implicit differentiation. So this, if I graph that, that is the inverse, just not written in nice notation. It's the inverse written in implicit notation, not explicit notation. We're trying to get it in explicit notation if we could, and that would make our lives a lot easier, but we can't. But we can still find the implicit derivative here, and that will give us the equation of our slope. So let's see here. If we implicitly derive here, we would say the derivative of the left-hand side, so the derivative of x equals the derivative of the entire right-hand side, 2y cubed plus y to the fourth. Now again, if you need to review implicit differentiation, just check out some of the previous videos. This right here, the left-hand side is equal to 1. The right-hand side, okay, that is 6y squared. But since we differentiated a y term with respect to x, we multiply by dy over dx. And then the same thing with here, we have 4y cubed, but we just differentiated a y term with respect to x, so that's dy over dx. We have to multiply by. So if we want to solve this, we would need to isolate the dy dx's and say 1 equals, let's see here, we would factor this, and we could say that factor a dy over dx, and we're left with a 6y squared plus 4y cubed. To solve that for dy dx, we would just divide both sides by this term here, and we would say that 1 divided by 6y squared plus 4y cubed equals dy over dx. Now, there is our derivative of our function that we're interested in. There is the derivative of our inverse function. Now, the problem is we were given, way up here, an x value. And our function is in terms of y. So we're still hit that problem of, okay, I can't just simply evaluate dy dx at 3 because 3 is an x value and these are all y values. So I still have to find the corresponding y value to this x value, which I have already found. We know that the corresponding y value is 1. So I can evaluate dy dx at 1. So dy dx at y equals 1. That is 1 over 6 times 1 squared plus 4 times 1 cubed. Does that look familiar? Well, I hope it does, because you get 1 over 10, the exact same solution. Now, is one of those ways easier? I don't really think so. I mean, you have to use implicit differentiation one way, and then you have to use this really funny looking formula the other way. I think they're both about equally as difficult. But that's another way to solve the exact same problem, get the exact same answer. Okay, but the crucial thing, I can't stress this enough. The crucial thing is this right here, this box right here, where I was really parsing out where is this 3. I was given the 3 to start with. 3 is in the domain of f inverse, which means 3 will be in the range of f, and then I have to kind of fill in the puzzle pieces, figuring out that, okay, if 3 is in the range of f, 1 has to be the corresponding x value in the domain of f, which means then 1 will be in the range of f inverse. So don't try to overlook that fact. This is the most important part on this screen right now, figuring out where your domain and range, how they relate between f and f inverse. Okay, let's look at this graph real fast. Okay, I actually graphed this one ahead of time, so I can. It's really easy to me to pull up real fast. So let's actually save that one first, and let's see here. So here is the graph of f. Okay, this is 2x cubed plus x fourth. Okay, 2x cubed plus x fourth. Now, notice it's not actually 1 to 1. So in general, the inverse function does not exist everywhere. You have to restrict the domain. So technically here you would have to restrict the domain. Say, look at the domain here from this point right, and that would work for us as far as making sure it passes the horizontal line test. But we're not really concerned with that, because at the point we're concerned with, everything is fine. So here is f. Here's f inverse. Okay? Notice it is a reflection across the line y equals x. Okay? So you have f and you have f inverse, and we have the point 1, 3 on f and 3, 1 on f inverse. So when I say the corresponding point between f and f inverse, this is what I'm talking about. If 1, 3 is on f, then 3, 1 is on f inverse. That transposed relationship is what I'm talking about here. So what I found was that the slope of f inverse at this point right here at 3, 1, I found that the slope was 1 over 10. If I use point slope form to find the equation of this tangent line right here, it's y equals 1/10 x plus 7 over 10. And there you go. So there is the tangent line at 3, 1. Now, also there is a reciprocal relationship between the slope at this green point 3, 1 and the slope of this red point 1, 3. That is, the slope here is the reciprocal of the slope here. Now we said the slope here was 1/10. The reciprocal of 1/10 is 10, which means the slope here is going to be 10. And I've already found the equation of the tangent line. It's y equals 10x minus 7, and there you go. So there is everything we just talked about. So just to remind you, the red curve right here, that's f. We know the equation of f. The green curve over here is f inverse. We do not know the equation of f inverse. We couldn't find that easily. But we used either implicit differentiation, or we used the method described in Theorem 3.17 to find the slope at this point. So the slope of the black tangent line at 3, 1, we found to be 1 over 10. We can also figure out, which we could figure this out otherwise, but we know automatically if this slope is 1/10, then the slope at this point has to be 10, even though we could have found that out very easily otherwise by just evaluating f prime at 1. Okay? So that's that. Now, what else do we want to look at here? Maybe look at one more example. Sure. Let's look at one more example before we do the trig stuff. Okay? Let's look at one where we actually could find the inverse function pretty easily. Okay? Let's see here. Let's look at f of x. F of x equals x squared. Now, in order to make this work out nicely, let's just say that x is greater than or equal to 0. That is, this is a parabola with the vertex at the origin. I'm just going to say, let's guarantee it's a one-to-one function by restricting its domain. Now, let's say I want to find the find the slope of f inverse at 9. So find the slope at f inverse of 9. Okay? Oh, actually, I'll do this. At f inverse of x when x equals 9. Okay? So just to be clear here, x equals 9. I'm talking about that is in the domain of f inverse. Okay? So if I make that little chart again like I've been doing, I would say this. I would say that I have some function f. Okay? It's x squared. I then have another function f inverse, which I haven't found yet, but we will find that in just a sec. We have elements in the domain being mapped to the range, and we have elements over here, domain, being mapped to the range. Okay? So this right here, that's saying that that value right there is in the domain of f inverse. So 9 gets mapped to something in its range. I don't know what that is because I haven't found the rule for f inverse yet. But if the 9 is in the domain of f inverse, 9 has to be in the range of f. And so the question is, what value do I plug into f to get a 9? And I think we can clearly see that if you plug in 3, if you evaluate f of 3, you get 9. So that means that f inverse is going to map 9 to 3. So if I just go ahead and apply Theorem 3.17, Theorem 3.17 tells me that f inverse prime of 9 equals 1 over f prime evaluated at f inverse of 9. But what did I just tell us, or what did we just find that f inverse of 9 is? F inverse of 9 is 3. So this is 1 over f prime at 3. Well, what's f prime of 3? I guess we could write what f prime is real fast. F prime of x is 2x. Okay, so evaluate 2x at 3, we get 1 over 2 times 3 equals 1 over 6. So there's the slope of my tangent line of f inverse when x equals 9. I don't even know yet what the inverse function is. Now let's verify that result. Because in this case, we can find the f inverse function actually pretty easily. Let's verify that result. Now the way we verify that result is by doing that process to find the inverse function. Okay, remember from algebra class we say y equals x squared. That's step 1. Step 2 is to interchange x's and y's. So x equals y squared. We then try to solve this for y. We take the square root of both sides, and we say the square root of x equals y. Now, I don't have to use a plus or minus there because I've assumed that our domain of f is only numbers greater than 0. Okay, or equal to 0, sorry. So there is my inverse function, f inverse of x equals the square root of x. Okay? So if I wanted to find f inverse prime of 9, I could just differentiate this and find, okay, what is f inverse prime? Well, f inverse prime of x is the derivative of this. Now, what have we found repeatedly the derivative of the square root of x to be? Okay, I'm not going to do all that all the way out. Oh, I shouldn't skip here. Sorry, I lied. I will do this derivative all the way out. It is x to the so you bring the, first of all, we would say that this right here is equal to x to the 1/2 power. So the power rule then says we bring that 1/2 out front, and then we reduce the power of the exponent by 1. So that's negative 1/2. So if we reduce this, it's 1 over 2 square roots of x. So there is f inverse prime. Now if I want to evaluate f inverse prime of 9, that was the original question. That's 1 over 2 square roots of 9 over 1 over 2 times 3 equals 1 over 6. So there we are. Exact same solution. So there we go. All right, so if you can find the inverse function, you can skip all this stuff over here. You can skip all of that if you can find the inverse function. The problem is that typically you will not be able to do this process right here. As we saw in both of the prior examples, you can't complete this process. In fact, that's what we're about to show with some trig functions. We will run into a roadblock trying to do that. Okay, so if you can just straight up find the inverse function, then do that. And then differentiate the inverse function and evaluate to find the correct slope. But the issue is that a lot of times at this step, you'll run into a roadblock, therefore you can't get that, and thus we are forced to use this process over here. Forced, okay? All right, so that is inverse functions and how to find the derivative of an inverse function when you don't know the inverse function, or in this case, when we did know the inverse function. Now, let's apply this to trig. Okay, let's apply this to trig and see what happens. All right, so let's see. There's our original result. The other results from this chapter are our trig derivatives, our inverse trig derivatives. Now, so here are 6 new things we need to memorize, and I'll show you where a couple of these come from. Okay, so these are 6 new derivatives you need to add to our list, but they're not hard. They look really hard, I'll give you that, but they're not as hard as they seem because they come in pairs. Notice here that arc sine and arc cosine, remember that's sine inverse and cosine inverse. Okay, so that's not the same thing. Some people get secant and cosecant and stuff confused. This is arc sine, which is sine inverse, and arc cosine. This is not cosecant and secant. 2 different things. Excuse me. So here we notice that these are essentially the exact same, except there's a negative sign with cosine, and there's not a negative sign with arc sine. Same thing here with arc tan and cotangent. They're the exact same derivative rule, except that the arc cotangent has a negative sign up front, and the same relationship exists with secant, arc secant, and arc cosecant. The only difference between these two is that there's a negative sign on the numerator. So you essentially have 3 formulas to memorize, and then you get the other 3 for free as long as you can remember, hey, they're the same thing, add a negative sign. Okay? Now, let's just pick one of these and show where it comes from. Let's pick arcsine. So arcsine we know is the inverse function of sine. But let's say we didn't. Let's back up a lot. Let's say we want to find the derivative of the inverse of sine x. But let's say, you know, we aren't familiar necessarily with the whole arcsine idea. Okay? Let's say that's our context here. Well, we could use those, you know, that technique from algebra that we were dealing with earlier. That is, okay, we know that y equals sine x. But let's say that we were going to use that technique from algebra and try to find the inverse of this. So what was the process? The process was, okay, step 1 is just to write your function, replace the function notation if necessary. So I guess I could have said f of x equals sine x up there, but that's no big deal. Step 2 was to interchange your x's and y values. So we would say x equals sine y. Now that is the inverse function, it's just not explicitly defined. That's an implicit version of arcsine. But we would want the explicit version for sure. But this thing is, what do you do now? Like, if you don't know what arcsine is, what do you do now? Well, you're kind of stuck because you're stuck trying to solve this for y. But let's use that process we did earlier by just differentiating both sides. That is, using implicit differentiation. So use implicit differentiation. Okay, so if we use implicit differentiation, what happens? Okay, so we say the derivative of the left-hand side and the derivative of the right-hand side, both with respect to x. Okay, so what's the derivative of x? Well, that's easy. With respect to x, it's just 1. What's the derivative of sine y? Okay, well, again, so we have to use like the chain rule here because the derivative of sine is cosine. But since we took the derivative of a y term, we have to multiply by dy dx. If we were going to solve for dy dx, like we always do with implicit differentiation, we would say that dy dx equals 1 over cosine y. But here's the thing, and that would be fine, okay? That would be fine if we were looking for a specific, you know, value, but we would run into that same process just like we did in the previous section where, okay, that's a y value, but we want to be able to plug in x value. So that's really annoying because we'll be given an x value. We'll have to make those 2 little charts I made several times showing domain and range of f and f inverse. We'll have to figure out, you know, if x is in the domain of f inverse, it's going to be in the range of f and all that stuff. We want to find this in terms of x, and we can do that. And here's how you would do that. Draw a little picture. Draw a little picture over here. What do we know? We start with y equals sine x. Y equals sine x. Excuse me, nope, we're starting here, sorry. We're starting after we swap, okay? We know that x equals the sine of y. What does that tell us? That tells us that y is some angle, right there, and that the sine of that angle equals x. Well, what is sine? Okay, sine is opposite over hypotenuse. So if sine of y equals x, that's the same thing as saying x over 1. opposite over hypotenuse. So x and a 1 goes there. But let's say I want to find this side of the triangle right here. And why do I even care? Because I want to know what the cosine of y is. If I can figure out the cosine of y, I might be able to rewrite this term right here in terms of x. So what's the cosine of y? Well, I need to solve using the Pythagorean theorem for this side of the triangle. Well, what's that side of the triangle? Let's just say, it's r. What does r equal? Okay, well, we could say that r squared plus x squared equals 1 squared, according to the Pythagorean theorem. If we solve that for r, we could say that r equals the square root of 1 minus x squared. Okay? 1 minus x squared, so... Okay, so now we know that cosine of y is what? Adjacent over hypotenuse. So cosine of y is equal to the square root of 1 minus x squared over 1. So just make that appropriate substitution now. dy over dx equals 1 over the square root of 1 minus x squared. And there we are. Now you might say it looks a little different. That's fine, because this is written right here in terms of the chain rule. So the chain rule would be like if you have the derivative of not just a y there, but if you have the derivative, if you have not an argument, not just a y, if you have an argument of like y squared, or any function there in the middle. Okay, so it turns out that all you have to do is replace the x with u and a du on top, right? A derivative on top, u prime on top. Okay, so that is where that rule comes from. I can show you. Let's just real fast look at another proof. Let's do tangent. Okay, let's do tangent. So if we were going to try to find, here, let's give ourselves a tad more room here. If we were going to try to find, let's see here, let's get a new color. If we were going to try to find the inverse, the derivative of the inverse of tan x. I'll say f of x equals tangent of x. Okay? Well, if I was going to follow that algebraic process of trying to find the inverse function first, we would follow those same steps again. We would say, all right, let's do that. Let's say write y equals tangent of x first. Interchange your x's and y values. This is that algebraic process. So x equals tangent of y. But now I'd be at that exact same process of if I don't know about what arctan is, I'm stuck here. But I can still implicitly differentiate. So I can't find currently, I'm assuming I don't know it. I don't know what arctan is. Okay? So what I do is I implicitly differentiate both sides. So I say, all right, let's find the derivative of x, and let's find, with respect to x, and the derivative of tangent of y with respect to x. Okay, so this is 1, just like we found before, and this is, okay, what is the derivative of tangent? It's secant squared. So secant squared of y times the derivative of y with respect to x, since that's a y term, and we differentiate it with respect to x. So if I'm going to solve this for dy dx, I say that 1 over secant squared of y equals dy dx. Okay, so let's draw another one of those pictures that we drew up here for the Arcsine derivation. Okay, so if we draw just another triangle, we know that x equals tangent of y. So put a y right there. So x equals tangent over y, so it's tangent of y. So tangent of y is opposite over adjacent. So opposite is x over 1, right? Because this can be thought of as x over 1. Okay. So what is the hypotenuse here? Well, it's just 1 squared plus x squared, right? Excuse me, the square root of. So the square root of 1 plus x squared. Okay. Now, what about secant? Okay, secant squared, that is. Okay, so what's secant? Okay, remember that's 1 over cosine. What's cosine here? So we could say that cosine of y equals, okay, cosine is 1 over adjacent. Okay, it's not 1 over adjacent. 1 over hypotenuse. Adjacent over hypotenuse. So 1 over 1 plus x squared, like that. So that's cosine. So what is secant? So secant is the reciprocal, is the square root of 1 plus x squared. Okay? 1 plus x squared. But now we have secant squared down here. So secant squared y is 1 plus x squared. So if I just make that substitution over here, 1 over 1 plus x squared equals dy dx. There is my derivative of arctan. So I could say derivative arctan x. Now let's verify that. 1 divided by 1 plus x squared. Now you might say, oh, it's not the same thing, but here, this is just the chain rule version, okay? Remember, if we have just a plain x there, this is the derivative. If we have like a function there, like say x squared, it would be the derivative of u over 1 plus u squared, okay? So that's it, okay? Now we could do, I did arcsine, I did arctan. We could do the exact same thing for the rest of these, okay? You know, there's 4 more to go. I'm not going to bore you to death with deriving the other 4, but that's how you would do it. Now, let's just do a couple examples here, okay? Let's do a couple examples of you know, inverse trig derivatives. Now, people usually hate these because they think it's so much work, so much memorization, that is. But if you just remember that these are all paired together, arcsine, arc cosine, arctan, arc cotan, arc secant, arc cosecant, they're all tied together with that just a negative sign. You only have 3 new things to memorize as long as you can remember the relationship. So let's just, I mean, these are really easy as long as you remember the rules. Okay, let's look at a couple. Let's look at arcsine. Oh, we need to find the derivative, not just there. So the derivative of arc sine 2x. Okay. Now, okay, this is a chain rule interpretation now, because you know arc sine of x is just the exact formula we derived earlier. But if you have arc sine of 2x, what we have to do is write the derivative of our inside function. That's our inside function. So the derivative of our inside function goes on top. That is u prime. So the derivative of 2x goes on top. And the denominator, well, what goes on the denominator of arcsine, the derivative of arcsine? It's the square root of 1 minus u squared. So the square root of 1 minus 2x squared. So that is 2 over the square root of 1 minus, oh, I guess we'll say 4x squared. And that's it. I mean, as long as you can remember the rule, they're really easy to come by. Okay, these derivatives are really easy to take care of, but you just have to remember the rule. What about, like, say, derivative of, let's say, arctan oh, let's say x squared. Oh, let's make it even more interesting. 4x squared. Arctan of 4x squared. Okay, well, we just talked about the derivation here. The derivation said it's if it was just a plain x there, it would be 1 over 1 plus x squared. But it's actually a 4x squared there. So it would be derivative of the u, our function u. There's u right there. So the derivative of u, 4x squared, divided by 1 plus u squared. So 4x squared squared. So what's the derivative of that numerator? Well, that's not so bad. That's just, 8x. And what's the denominator? That's just a slight bit of algebra there. That's 1 plus, let's see, 16x to the 4th. 4 squared, and then x squared squared. Yeah, 16x to the 4th. Again, super easy, guys. Just you have to remember those the 6 derivative formulas. Let's look at a little bit harder. The derivative of arcsine square root of x. So again, we have a function here. So we have to use the chain rule interpretation. The chain rule says, all right, well, it's actually the exact same thing as here. We have the derivative of the square root of x over the square root of 1 minus the square root of x squared. Okay, so let's see here. We get, all right, let's see, the square root, the derivative of the square root of x. We found that on several occasions. In fact, we've already done that today. That is 1 over 2 square roots of x. Now that right there on the bottom, that's just 1 minus x, right? Okay. Now we need to simplify this a little bit. We have a fraction times a fraction divided by a fraction, rather. So we could say this is equal to, let's see, 1 over 2 square roots of x times the square root of 1 minus x. And I guess we should combine those roots, I guess. That would make it look a little better. We could say that's 1 over 2. Now remember, we have the properties of radicals. It says, if we have, these are both square roots, we can multiply their radicands. So it would be like this, x times 1 minus, times 1 minus x. And I suppose one last little thing there would make it look nicer. We could say this is 2 square roots of x minus x squared. Yeah, I don't know if I really prefer this version or that version. They'd probably both be fine on a test. But I think I might personally prefer that version better. It looks a little nicer to me. Okay. Oh, what about one more? 1 or 2 more? Well, let's just make it 1 more. We've been talking long enough today. The derivative of, let's see here, arc secant. Arc secant of e to the 2x power. So notice here, I didn't give us any of the plain ones with just an x in there. If we did, if this just had an x there, so I'll make this 2 examples. If we just had an x here, the derivative of arc secant, if you just have a plain old x there, that's easy. Is 1 over the absolute value of x times the square root of x squared minus 1. That's if there's just a plain Jane x there. All right? But if there is a function there, well, we have to do the top of the fraction is going to be the derivative of e to the 2x, that's going to require a chain rule. It's not a hard chain rule. Okay? And then the denominator, though, is the absolute value of your function, so e to the 2x, times the square root, of e to the 2x squared minus 1. Okay, there's a little bit of simplification required there. So what's the derivative of e to the 2x? Okay, so it's e to the 2x times the derivative of the inside function. So that is 2e to the 2x. If you need to review that, just check out some of the prior videos. Okay, it's the chain rule where the inside function is 2x, the outside function is e to the x. So you take the derivative of the outside function is e to the x, evaluate the inside function, so you get e to the 2x, and then you multiply by the derivative of the inside function, so the derivative of the 2x is 2, multiply those things together, you're good to go. Now, here, I think we can realize, to make this look a little better, that e to the 2x, that is always, always positive. Think about the graph of e to the x. You know, the graph of just plain old e to the x, that looks like, you know, something like this. Okay? So it's always positive. It never touches, it never gets to 0, and it never goes below 0. So we could say that forget about the absolute value signs, because the absolute value of a positive value is just that value. So e to the 2x times, okay, what do we have here? Okay, rules of exponents say that's e to the 2x squared is e to the 4x. E to the 4x minus 1. Oh, yeah, that's as good. Oh, wait. We have e to the 2x. Sorry, I almost missed that. We have e to the 2x, e to the 2x. So that is this whole thing is equal to just a 2 on the numerator over e to the 4x minus 1. Oh yeah, that's a lot better. Sorry, I almost missed that glaring cancellation there. Those cancel out. Cool. So there we are. Again, guys, as long as you are diligent in memorizing these 6 new derivative formulas, which really only require you to memorize these, if you can then remember that arc sine and arc cosine are paired, arc tan and arc cotan are paired, arc secant, arc cosecant. As long as you remember these are paired up, then all you have to do is add a negative sign to each numerator to get this side over here, then you'll be fine. Okay? You'll be fine. Just make sure to really get some practice in, and all will be fine. All right, cool. That is section 3.6. Pretty short, pretty sweet. You know, I kind of did extra examples here for you. If you need any more help, just feel free to email me, and I'll gladly help you with. I'll gladly help you clear up anything you need help with. All right, have a good one.